The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
This easy, and it's mostly to get you set up. You know how Stellar works, how you set up your own website. You know, make sure you have a camera that you can use. Make sure you have a way to transfer your images to your program. And as I said, it's completely up to you what environment you want to use. You want to use Java, Flash, C++, Photoshop, Basic, Japanese, whatever language you want to use for your programming. It's perfectly fine. But make sure you show me your own images, not images captured from somebody else or from the internet, but something that you have taken yourself, some photos you have taken yourself. Any other questions about the assignment? And so we'll have, for the graduate, for 531, we have 4 assignments, so 3 more after this. And for 131, we have 2 more assignments after this. While this is getting set up, I'm just passing around a UV light demo. Who has it right now?
I did.
Okay, good.
Yeah. Here,
Yeah. So why don't you demonstrate the concept to everybody first? So when it goes around, they know what to look for.
Okay. So
You have to show the magic trick. You have to show it's white first.
Sorry. So you see almost nothing, and then you light it on. There are actually a lot of things that do this too. My driver's license, Massachusetts driver's license has the Massachusetts state seal in it. Is that visible? Yeah. And usually most credit cards do. It says Amex.
So this was a SIGGRAPH paper in 2007 on how to create ultraviolet inks. So inks that respond to ultraviolet light. That are color.
Yeah, definitely the card technologies are older, but
this is color.
Yeah, you actually see in many passports and visas in particular, especially the smaller the country is, the more colorful the UV image of the visa is. Law that I observed. But you sometimes see red and green and sort of purplish colors. But I've actually never seen basically a full color thing like this before.
Yeah,
that's pretty neat.
And also, your if you go to a club, a lot of them use UV light. So if you haven't used the right detergent on your clothing, or if you had a stain that you think it doesn't look in the visible light, but you go to a place where you want to be hip.
I actually have a UV light LED on my key.
Oh, so before you go you stand in the line, you check yourself.
Yeah, exactly.
Yeah, you're cool for this place.
Yeah.
Yeah. So if you become expert at playing it with ultraviolet light, and you like to have this in your hand all the time, there are lots of jobs. You could be the guy who checks, at the entry at the airport at the security line. He's checking your card, or you could be a bouncer. Lots of job opportunities.
Or a banker, right? A lot of the dollar bills.
That's right.
$20 bills and up have a UV strip.
Exactly. So the theme for today is going to be lighting and different kind of illumination, and hopefully it'll make you think. With today, the budget is I think less than $5,000, unlike last time. I think it was well over $60K last time, and we'll show you interesting things you can do with illumination. As soon as my reboots and comes back up. While this is getting set up again, let me show you some other toys. So my collaborator, and Rohit is, if you can just hold the book and show it to everybody. This is the book that I and my co-author Jack Tumblin we are coming out with, called Computational Photography. And the way Jack likes to describe the scenario today for cameras and photography is, it's a lion who has been shackled for a long time, and if you just put this lion out of the cage, it doesn't know what to do. It just stands there and just looks around. Even an unshackled lion doesn't know how to exploit the freedom. I think it's the same situation with photography today. We have gone from film to digital, but even today, when we think about cameras, they're trying to mimic how this camera will look like a traditional film camera, a digital camera. Even cell phone makers who have complete freedom on how to create cameras and form factors, they're trying to create an experience that's somewhat similar to a film camera. They have a shutter at the same location, and they expect you to hold it with two hands, and so on. Like very few of them allow very single-handed interaction. I just want a camera that I can squeeze, or I can tap, or I can shake, and then after 5 seconds just take a photo. It can do all these other things, but they still want us to do this two-handed interaction where everything is stable. The button is off-center, so you cannot even hold it with one hand. You have to hold it with two hands, so you can press the shutter and so on. So this is how the world works. You always are dealing with the legacy of what came before. And really a classic example, something that makes me, is really squirm, is look at this beautiful camera that came out from Nikon in mid-90s. And this was one of the first kind of digital camera that professionals thought it's okay to be seen with. Because they had this whole debate about our digital will never catch up with the resolution of the film. These are the same people who still hold on to the LP, saying CDs are digital and they don't sound the same as LP records. But anyway, this camera, which is supposed to be digital, if you cut it open, what you realize is there is still place. This is a digital camera. There's still place for a film cartridge. Okay, all they did was they removed the part where the film cartridge is and where the film slips, slapped on a digital sensor, built extra electronics at the bottom, added some electronic connectors. But why bother? Because people still like the same form factor and all that. There's still place for film in there. It's just mind blowing, and this is how it works. And so a lot of times when people say, "Wow, a billion people have cameras, and what is going to change about it?" Hopefully through this class you'll realize it's just a wide open world. There are certain fields that peak. There is a lot of innovation and research, and then they mature, and there is not much more exciting about those fields. But there are certain fields that just continue to grow, and imaging is just one of them. So just look for the space for cartridge here, and if you look sideways, this is where the film wraps around. And so you can take pictures of this and add to the notes. I'm just going to spend the first few minutes going through some of the fast-forward preview items we didn't get to cover last time, and then come back and talk about today's topic. We were here somewhere last time, where you can create these cameras where instead of having a expansion, instead of having an autofocus blur that extends like a disc, you can create lenses where when it goes out of focus, the point squared function actually rotates. This is a rotational point squared function. And again, this is just a teaser, so we will study this into detail. And this is very powerful, whether it's for photography or for scientific imaging or for real-time HCI applications and so on. And then we discussed about the duality of particles and waves, and we will be discussing that a little bit. And then we'll talk about these new types of cameras that are being designed, where you can create a 35 millimeter lens, including the sensor. The whole package can be built with the thickness of just about 5 millimeters. And so they're building these lenses where light comes in from the annulus around the edges of the lens, and light actually reflects around, and the image is formed in the center. And this is how many of the Sony, what's the Sony brand for cameras? CyberShot, yes. works as well, where the sensors is actually for the Sony cameras, the lens is over here, but the sensor is actually all the way back in the bottom. So light reflects around, and the image is captured at the bottom. That's why the cameras are so thin. So the dream of a flat camera is something we'll be looking for. And again, by making flat, I mean the new iPod Nano is 0.25 inches thick, and it still has a camera, and that's because they're using crappier and crappier lenses. So instead of just creating a straightforward design where you have a lens and behind that you have a sensor, if you have a lens where with addition of this concentric reflectors, an image is found in the middle, then effectively you have a 35 millimeter lens with optical parts that's folded in. So we'll be looking at a lot of these interesting designs that I'm sure you will see in products coming up. And then we'll look at, again, some really interesting lenses. So a traditional lens is some form of a convex or concave lens, but the new lenses are just flat. Their front and back profile is just flat. So it's very easy to stack them, very easy to put them in modern devices. And the way they work is not by changing the thickness of glass, but by changing the refractive index. So the refractive index is high in the center and very low in the edges. So by doing that, they're effectively creating a lens. And that's actually how a lot of flatbed scanners are built as well. So we'll be studying that. Very briefly, photonic crystals and how they will change imaging. Schlieren photography. We saw the picture last time. We'll study how Schlieren photography can be built. Polarization underwater. And there are these really interesting cameras that are coming up. I can see if the lights can play it around. So, see the slightly better. So these are polarization cameras where instead of adding a polarizing filter in the front of the lens, the polarization filters are actually on the bare mosaic. So a typical camera, as you will study, will have very tiny RGB filters in front of each pixel. So every alternate pixel has red, green, and blue filter. And here, actually, they have different orientations of polarization: vertical orientation, horizontal orientation, plus 45 and minus 45 degree orientation for polarization. And from that, it turns out under certain lighting conditions, such as sunlight, light that's reflected from vehicles or from faces is partially polarized. And they can look at how the light is polarized in all these 4 different directions. And from that estimate the orientation of the surface or the surface normal. And from that they can create a 3D model. So it's pretty exciting. They're getting a lot of money from the government for detecting vehicles in complex backgrounds. So this might come in a consumer camera. It might come for scientific imaging. And there's some really interesting sensors. I think we talked about this very briefly last time. Compressive sensing. We'll spend a lot of time discussing compressive sensing. There's a lot of hype about it. We'll try to understand where it works, where it fails, and what's the power of compressive sensing and where it can be exploited. Some other bizarre photos you may have seen are near a photo finish in sports photography. So this photo looks like an ordinary picture. Here's the winner of this, I believe, 100-meter dash. But if you look at people behind, they have really strange anatomy. Look down here. Anybody has a guess what's going on? There's another one with even more distortions. Look at the leg of this, and that's the finish line. This is the photo finish picture in sports photography. Look at the legs here. Yes?
Because the sensor is scanning line by line.
Exactly. The whole photo is not taken at a single instant. The photo is taken actually one line at a time. As you can see, all the athletes, when they try to finish, because the shoulder, the moment you cross the shoulder is when it matters. So as you can see, when they finish, they all have their body leaned forward, right? So clearly, not all of them are finishing at the same instant. But so this particular line, for example, captured first, and then the next one, and the next one, and the next one. So this whole picture was captured over a whole second, but it's actually running at 2,000 frames per second. So in 1 second, you're capturing 2,000 lines, and they're simply placed together to construct this picture. And this is very useful because for the judges, for the referees, they can just look at this picture and figure out exactly when every player had crossed the finish line. And it's a nice summary of the finish of the race. But not finish at any given instant, but finish of every instant. And so if you look in the background, you'll see that there are no vehicles, there are no big signs. Same with the track here, and that's because we're capturing the same exact line in the camera and just capturing the same one again. So imagine taking a photo, throwing away all the pixels except the center line, taking another picture after 1 by 1 2,000th of a second, again just keeping the center line and just putting it together. So very interesting photography. And I believe I saw a product on, maybe it was an iPhone app or one of the mobile phone cameras, where they're creating this new kind of fun photography, where instead of taking a photo in a single instant, you release the shutter, and it actually does a very slow rolling shutter. So it's actually a video camera that exposes the first line, then the second line, then the third line, and so on for every frame. So I can release the picture, and I can simply turn in front of it. And what you will see is the top of the picture, my forehead is being seen. In the middle, it's side of my face, and at the bottom, it's the back of my head. So it's very beautiful pictures that can be created with this. But in this class, maybe you can convert a video camera into some other interesting projection of this XYT volume, right? Because a video camera is XY pixels, and we're capturing it over time. So it's a 3-dimensional data set. And a final photo is actually some 2D projection of that. And this is one type of one way of projecting it. But we'll study how there are some other ways, either for scientific imaging or for artistic photography.
What type of lens they use?
They usually use standard lenses because they still have to create. If you're looking at a very narrow line of view direction, you still have to form an extremely high quality image. So you cannot use a cylindrical lens or anything like that. So they still use a traditional lens for that.
So is this the main difference between a video camera and standard cameras?
In terms of its, there are several differences when it comes to electronics, of course. So, for example, a camera like this on a cheap device is actually a video camera. And when you release the shutter, or any cheap digital camera is actually, still camera is actually a video camera. And when you release the shutter, it takes the next frame and captures that as a real photo and gives it to you. But it's constantly running as a video camera. And that's why on the viewfinder, you can see the video of what's being captured. So even if they're selling it as a digital still camera, and even if they don't have a video mode, it's actually a video camera. And then there are more purists who build, SLRs and so on, and they say, no, it is a digital still camera, and you must see through an optical viewfinder. But just like the people who make the camera we saw, those people are a minority. And all this snobbishness about when you have an SLR camera, you must have a mirror is also gone, fortunately. So that's kind of the fundamental difference between still camera and video camera. But there's still an issue of bandwidth, and that comes to storage and processing, how quickly you can capture, even if you're exposing the whole sensor. So typically you might have a digital still camera that's 6 megapixel, but the video is only less than a megapixel. And that's mainly because of bandwidth and storage and so on. But it's not really, it's just an electronics issue. So there's no reason to, in the future it will be all fused into, once the bandwidth and storage issues become not so critical, They will just fuse into one single device. There are already cameras, I believe, that once you release the shutter, you could be in the video mode, and then you release the shutter, it just stores some of those frames. So that's straightforward. So in terms of optics and image formation, there is no difference. There are some other differences, of course, in terms of noise. So if you know that for a digital still camera, when you release the shutter, usually a mechanical shutter opens and closes to, integrate the light for a finite duration. But clearly for a video camera, there's no mechanical shutter opening and closing for each frame. So why don't they just do that for digital still cameras? Why not have why not get rid of the mechanical shutter altogether and just do an electronic shutter? And again, purists want that sound, ka-ching, ka-ching. But there's absolutely no reason to do that. And nowadays it's true that a lot of cameras have focal plane shutters that sometimes are mechanical and sometimes are just electronic.
Is there absolutely no reason to have a mechanical shutter?
So exactly. So sometimes you have issues like just thermal noise. So if you're taking a picture that's 15 seconds long, then you don't know how the camera is going to behave, how much noise is going to collect over 15 seconds. So a camera maker has a very good model of what the noise will be if you take a very short exposure photo, like under a second. But if it's a 15-second long exposure, depending on what conditions you're in, how warm your hand is, all these things are going to change the noise properties on the sensor. So typically they'll take two pictures. They'll take a 15-second long picture with shutter open, and then they will take a 15-second long exposure with the shutter closed, and they'll subtract the two images to get rid of the noise. Because there could be noise that varies over the frame of the sensor. So every once in a while it's good to have a completely dark conditions created mechanically. But again, that will change over time. And I'm sure they'll come up with solutions where you don't have to do this extra measurement to figure out the noise in the system of doing the subtraction. I mean, communication world, right? I mean, you have to deal with noise all the time, and you don't always transmit the data twice. So I'm sure we can come up with some intelligent encoding. Maybe every fifth pixel is being used for measuring noise, and other pixels are being used for capturing photo. So there will be some interesting encoding mechanisms there, I would imagine. The City Block project, that's Gaurav Garg, he was my intern. And this was a project that started with Augusto, forget his last name, Augusto Roman, I think. And they started this project when they were a grad student at Stanford, did an internship at Google, where they came up with an idea of mounting a camera in a truck and just driving in Palo Alto, and again using a very similar idea of just taking the center pixel of every video frame. So if you can imagine, you take thousands of pictures and take only the center column of each image and just put it together, then you have basically created this orthographic camera. It's a panorama that just goes on and on for a facade of a street. And they applied some other interesting algorithm because if you have streets or people or cars that are moving or in front of the part that you care about, then because of the parallax between multiple views, you can eliminate them as well. So they put all these things together. That was their City Block project. And you get very interesting distortion artifacts and so on, but it looks beautiful. And what Augusto tells me is that this is what they pitched for Google Street View as a representation, because right now it's all discrete. Right? You jump between one bubble to the next bubble. And what he tells me is that the reason why they didn't choose what he did in his thesis and they went for this traditional bubble model is apparently in user studies they realized that people get really confused when you show them pictures like this. People are more comfortable with jumping to the next bubble and then looking around and then jumping to the next bubble and looking around. It's kind of odd to me because I would be more comfortable looking at something like this. But this is what they have right now. Of course, the new Google Street View system actually has a lot of additional sensors. They have GPS, they have compass, they have a LiDAR that's actually taking 3D images of all the cities. So if a Google truck is going by, cover your eyes because they're shooting lasers. I'm just kidding. It's eye safe. but they have 3D models. And the reason why the 3D models are not available to us as on the browser is because they haven't figured out how to use this, petabytes of data and how to transfer that and make it available in a streaming fashion. But again, when that problem is solved, we will see 3D models that are exploited for all kinds of interesting purposes. And this year I was on the SIGGRAPH committee, and there were just ton of papers on what you can do with street level imagery, because this is becoming a very hot topic right now, which is good and bad. If it's already hot, it's probably not worth pursuing it because there are too many people doing it. But for a course project, it's perfectly fine to do, and you might be able to come up with a great idea for a SIGGRAPH paper. We'll be studying a lot about motion deblurring. This is actually a picture we took in Kendall Square. And we have cameras now that can take highly blurred images, motion blurred images, and recover a sharp photo in post-capture. So last time we saw focus deblurring. This is motion deblurring. And the way it works, and here's another example where you might have an aerial imagery scenario, an aircraft that's flying sufficiently low, and with a sufficiently long exposure, you'll get a blurred photo. But again, using this technique I'm going to describe in the next slide, you can do motion deblurring, same for cars. And the basic idea was, instead of taking a photo where when you release the shutter, you open the shutter and keep it open for say 100 milliseconds and close the shutter and get one photo. Instead of that, you release the shutter and then you open and close it multiple times, and at the end you still get one photo, but you have stopped and started the integration of light multiple times in between. Okay? And of course, if you do that with a mechanical shutter, you'll probably void the warranty and the camera will be unusable very quickly. So instead of a mechanical opening and closing of the shutter, we used an LCD, actually a ferroelectric LCD that becomes transparent or opaque. So when the LCD is, of course, opaque, you block the transmission of light, and when it's transparent, the light goes through. And that encodes the motion of the object. So if you have a point light with a traditional camera, if I move the light very fast, you will see a streak in the photo. But with this camera, you will see like a ham code. You'll say dash dot dot dash dot in the screen, and that actually preserves high frequency information in the scene. And as we will study later, it allows you to reconstruct the original image and recover the sharp features. And we'll study this in the frequency domain. We'll study this using linear algebra, and we'll also study this using pure intuition. So those of you with different backgrounds hopefully will be very comfortable with many of these concepts. Now, this is a very worrying trend for sensors. So 1994, pixels were about 9 microns wide. Okay, a human hair is about 50 microns, so it's 1/5 of the width of a human hair. And the way you sense the color is you put a filter, green, blue, green, red. So and that's the Bayer mosaic. And we'll study this later again. But over time, the size of this pixel is shrinking because you want to buy a phone that has 5 megapixel, but it has really tiny focal length, and it's fine. So the sensor is shrinking, and the camera makers want to produce a lot of sensors from a given wafer. So you have a wafer of a certain size, you want to slice it and dice it, and then put it into each of the cameras. The more you slice it, the more pieces you will get, of course. And so the logic is, if you keep shrinking these pixels, you can keep shrinking the size of the overall image sensor. So right now we are down to 2 micron, 1.5 micron. I just saw a paper from Sony yesterday where they're claiming 0.9 microns. And what's the wavelength of visible light? 0.4 to 0.7 microns. So let's write this down because we'll be talking about this all the time. So this is is 50 micron. That's width of your hair. This is 10 micron, 1 micron. And if you zoom in here, 500 nanometers. This is 1 times 10 to the minus 6 meters. 500 nanometers, and blue is here, green is here roughly, and red is here, or 400 or so. So that's the wavelength of light, all the way down here. Now the pixel itself is 0.9 micron, right? And the wavelength of light is, in very simple words, really, really close. And so this is a challenge, and as we'll study later, because of the limitations of diffraction and other laws of physics, it's getting very challenging to do reasonable imagery with this type of sensors. And again, we'll study how people are thinking about this in a very traditional way, and some other teams are actually trying to exploit these sensors in completely unique ways. Now, there's a new design where people are claiming that by using a pixel that's less than 1 micron, by the way, compared to this pixel, let's say this is 10 microns and this is 1 micron. The amount of light 1 pixel will capture is reduced by what factor? By a factor of 100, right? So with my phone in 1994, if everything was the same, if I could take a picture in 100 milliseconds, now how long will be my exposure time? It will be 10 seconds, right? But clearly, over the last 10 years, the exposure time of a typical photo hasn't changed. Otherwise you'll have a camera shake because of because of the jitter in your device. So clearly, the technology has improved where the pixels have 100 times less area to capture light, and still we're able to get photos with roughly the same exposure time. So in a way, the light gathering capability has improved by a factor of 100. Not really, but it's about that order of magnitude, and there are a lot of software tricks that are being played to kind of compensate for the noise in such tiny sensors. So we'll study this issue quite a bit. One common theme throughout imaging is the two things you need. You need a lot of light. You always want a lot of photons to take a good picture. And number two is you would like to have negative light. And this may sound strange, but people who work in radio and other fields, they are blessed with negative energy. And people who work in optics always have to worry about creating negative light. And as we'll go through the class, you'll realize that if somebody invents negative energy for light, it's like the invention of zero. To just represent nothing. Negative light. Yeah, a photon that has negative energy. You have an idea? Think about it. Very hard. Yeah, you'll get multiple Nobel Prizes. All right. And then there's some really interesting biological creatures that we'll be studying. Animal eyes. So a dragonfly or a krill has this compound eyes that this is the simulation of what this guy is looking at. It's proliferating thousands of images, probably not of that good quality, and they're used for very interesting applications. So we'll study that as well. So there's a project called Tombo in Japan, which I believe stands for Thin Observation Module by Bound Optics, but the word Tombo means shrimp in Japanese. What does the word Tombo mean?
Dragonfly.
Sorry? Dragonfly. Sorry, dragonfly. So it's a nice play on the dragon. I should remember this. It's right on the slide before. And so again, you have a single sensor, and you have multiple tiny lenses, and this is placed really, really close to the sensor. And the idea is that if you have an object and you have plenty of tiny sensors right next to plenty of tiny lenses next to the sensor, then again you'll form thousands of images, and from that you may be able to do something interesting. We'll also look at time of flight cameras. We saw last time one of the 3DV cameras that uses time of flight to compute depth. So how fast does light travel? 3 times 10 to the 8 meters per second. But what did we see last time? What did we?
1 feet in nanosecond.
1 foot per nanosecond. And sound?
1 millisecond.
1 foot per millisecond. Okay, just good numbers to remember. And so these cameras will study how they work. And it's quite possible that this type of cameras will be available in really cheap devices. I'm talking about devices that are less than $100. So Microsoft Natal is likely to have a 3D depth sensing camera very soon. And Sony iToy is also likely to have one. In fact, Sony iToy has been, Richard Marx, who's the kind of spiritual leader of iToy, has told me multiple times that they will come out with a 3D camera anytime now. And they've been testing it. They just want to make sure the cost is low enough to make it happen. So this is a very exciting time for imaging. And those of you who think, oh, we already have 1 billion cameras, how much is it going to change? You'll be extremely surprised what you will see just in the next 2 to 3 years. And these 3D cameras are also being used in TV studios, where you may want to insert some virtual objects in the scene. So traditional mapping, you just replace what's the background. Maybe you have a blue screen and you replace the background. But here, you can put something in front and behind the person with the right occlusion order. So we'll study these things. We'll be spending a lot of time about cameras for human-computer interaction. This is a topic of always a lot of interest. And we'll look at different types of cameras. Camera looking at people, camera looking at fingers, such as the frustrated total internal reflection, FTIR, how optical mouse works, anathopen, and so on. Different types of motion capture, and so on. And we'll also look at what are the type of camera-based HCR projects that are interesting, and some of them are just very 20th century. Okay, and this is very interesting, because if you go to places like SIGGRAPH emerging technologies, where people are really combining the latest generation of algorithms and hardware, you'll see over time which projects are interesting and which projects are just stupid and boring. Right? And there's some really, really common ones. And those of you who are doing this for projects is perfectly fine. But if you're thinking about using it for research, then think about it. This is something you should avoid, because it's been done to death. The most common one, I have to say, is where something moves and the music changes. Just get out of that business. All right. Another one is you're going to write some HCI application where it's going to depend on detecting, some skin color or something. It's not going to work. Okay, you might be able to show it as a demo, but as research, it's not going to work when the lighting changes or the orientation changes and so on. Another very common excitement is I'm going to take a light and put a stereo camera and track it and create a 3D path of it. Done to death. There are things you can buy for $100 that will do it for you. And when there's a product, it's not worth doing research on the same problem. Again, segment a finger or a face by putting some kind of a glove or something for segmentation. Some artistic interactive displays. I can wave a hand and change something. Don't worry about it. A lot of people know how to do it. And the problem with a lot of these demos, as you'll see, is that you can build this demo and you will be able to get some people excited about it, and that will give you this positive reinforcement that, oh, this is the kind of stuff I should be doing, because you can impress some people all the time, and you can impress all the people for some time, but not all the people all the time. And of course, the word was not impress in the original quote. And just remember that. So, there's a problem here. Let's see if I can fix it. So what we're going to do in this class is...
What's the solution?
Yeah, exactly. You have to attend the whole semester to listen.
I have a quick question on the boring HCI camera thing.
Right.
What's the current status of like the gaze estimation work in that? It kind of falls into that.
Right. Yeah, we'll talk about that as well in the class. And there are some really good solutions, but I think it's still, gaze tracking is still a pretty challenging problem. So I think that's worth still exploring. And again, this is not an offense to anybody. If you're doing it as a class project, it's perfectly fine. But let's just be honest. It's when you are an acquaintance, we praise each other's work, and when you're friends, we criticize. And we're just going to be very, very honest about it and see what we can learn and what we can do next, right? So the solution is you have to change the game. You want to try to build things that are robust. They do kind of things that nobody else can do, and they allow you to do things that are not possible with today's cameras, right? So we just want to use smarter sensors, smarter processing, and what you create should be just magic. Not in terms of its application, but in terms of its basic building blocks. And hopefully through this class you'll realize there are hundreds and hundreds of solutions that you could be using instead of using some cheap camera that's available, and just because you have the SDK for it, or just because the device is available, you're using it. Let's get away from that, and let's try to build something that's unique and new. Okay. Any questions on this one?
Question?
Yes.
So, if you want to build stuff like building a new camera or building like changing the motion or the shutter and stuff like this, so what other components are available?
That's a great question. So let me just repeat Dina's question. If you really want to do all these things, what are the components that are available? Can I just slap together a sensor and a light source and all this electronics? The answer is it's not always that easy, unfortunately. It's not, I wish Canon would just come out with, a Lego for cameras and just sell that. And I'm sure they'll sell, millions of those. But because then you can create your own things. But unfortunately, it's not available. At the same time, what I've seen, especially at Media Lab, are people are extremely innovative, and they go and pick pieces from different places. I think Dan has been looking into that. And SparkFun has been very supportive. They sell camera modules for $3 to $9 now. You can buy a full-fledged camera for $3. Unfortunately, there's not much you can change about it. But then you can go to companies like Point Grey and buy a little bit more expensive solution, maybe $500 to $1,000, and they'll give you more access to it. So, all the projects that we do here, we are not building our own sensors. We are not building our own chip, processing chip. We are putting pieces together from different places. And, we are definitely on the bleeding edge. So if you want to build something unique, there is no solution available. You can't just buy a kit right now to do it. I know JB has been interested in building a, what do you call it? What kind of camera? Open source camera? Or?
Yes, and I'm actually working with a company in the university that is doing kind of Lego for camera.
Excellent.
The glass, but it's very slow and it's still it's a line of box.
Right.
It's not this small module that you can program in wireless and everything, but
right.
It's already a good start to go to think of that.
Right.
So,
yeah, so so there are a lot of efforts in that. So I'm glad to hear about your work. And then Stanford, Professor Mark Lavoie and his group has been also proposing an open source camera architecture, and they also ran into the same issue of how can they get some of the chip makers and lens makers and all that excited to put this together. So they're just getting started, and I hope that movement will continue. We have a lot of our own plans here, which we'll be disclosing in coming weeks. And it should be possible to, and there was a time when it was very cool to hack around with your car, right? In the 70s and 80s. Like, you're a cool guy if you fix your car and put new things. Now people say, okay. And then there was a time when it was very cool to build electronics, build cool electronics, do something with robots. And people say, yeah, that's okay, I can just buy it. And what's going to happen now is we're going to get into the physics of these things. Not just the chemical engines and the electronic hardware, but we're going to get into the physics of it. Whether it's UV light, whether it's chemical elements or whether it's a sensor, and the next generation of kids who want to be cool are going to build things that just create magic. So I'm really excited about this whole area. In fact, there's a group at Columbia University, Professor Sri Nair, and he's putting together I forget the name of the project, but it's also kind of a Lego for cameras, and that's going to be a lot of fun. They're trying to create a whole high school curriculum based on cameras, so it's very exciting. So we look at how Jeff Hahn's project was developed, and remember his paper came out only in 2005. That's the very first time he disclosed it, and after that, as you know very well, it's everywhere. John King is using it on CNN to see how Obama is doing versus McCain, and it's just everywhere. Beautiful piece of technology, very old idea that's used in lots of other environments, and we'll study that. And
Can I
going.
ask you a quick question?
Yeah.
So, if this is a camera,
Mhm.
are sort of all touchscreen displays essentially cameras?
That's a great question. So this one, in a way, is still using a traditional camera. When John King is playing on CNN with all that thing, what you don't realize is that behind him, he requires a lot of space to put a camera and a rear projection screen. Right? It's not just walking up to some thin LCD and playing with it.
I mean, so if I have two pieces of glass that I'm pressing on,
Right.
and that I'm detecting, which wires are actually touching each other,
Right.
I've never thought of that as a camera before. So I'm thinking about it right now as maybe it's kind of like
Certainly. That's the way you should be thinking. A camera is not a two-dimensional sensor. It's just zero-dimensional, which is the point, one-dimensional, a line or a curve, two-dimensional, three-dimensional. We'll see eight-dimensional sensors there soon.
But of course, we usually think of cameras as sensing light, not sensing, pressure.
Mm-hmm. But you can convert pressure into light. So Kimo, I don't know if he's here, he'll come and give a talk about how his device works. And what they basically do is they have created this surface. It looks like Jello, and they have built some really, really beautiful demos. I believe he's going to come in a couple of weeks and show this. And what this Jello-like device does is I can put my finger on it, and it transfers that into a highly visible impression. And then, in very simple words, he simply takes a photo of that with changing lighting direction. And they can create this very, millimeter or multi-micrometer scale objects, and then take photos of that. So, you always need a transducer. A camera is converting photons into electrons, but you could have other transducers, pressure into electrons or pressure into photons. Yeah.
I think what he's talking about is resistance grid or capacitance grid, multi-touch interfaces, and those don't have inside.
Well, I mean, but a camera is sort of some generalized, we sometimes think of any kind of sensor that can give rich information as a camera.
Right. Maybe the other way to phrase is that what sensors can give you visual information, and then yes, whether it's a resistive or capacitive or inductive, it still could give you some geometric information. So, but although we won't be studying them as such, we'll be studying more based on whatever happens to photons. But then, going beyond that, how can you create something out of a thin screen? And this is Matt Hirsch. That was his class project last year in this class. And he started thinking about it in the class, and he built an initial prototype for his final project. And this, of course, now has become a SIGGRAPH paper, part of his master's thesis. He won the student research competition this year, just out of this class from last year. And we'll study how that works. And then we'll study things like this Anotopen, which has a grid of dots that are slightly misplaced with respect to the center of its position. And every block of, I believe, 6 by 6 is unique. And just with this grid of 6 by 6, they can create sufficiently unique codes so that if you create paper with this code and just lay it out, it will cover half the land area of the US. So they can print many papers with this codes printed on them. And a pen has a camera that looks at this 6x6 code and figures out its unique location in a coordinate system that could span 1,600 kilometers by 1,600 kilometers. So it's really unique. And then this way you know where the pen was on which page and which XY coordinate. And this is a way to basically record the strokes that you will try. Yes, Jim?
It's also, I work in this company, there are 200 people and more than half are lawyers. There are 250 patents on this. So it's interesting to see also the context of this. So it's very difficult actually to hack it or to be able to go beyond the SDK or what they propose you to do.
Right.
So it's a very challenging sport.
But I think SET has license.
You have license, but you cannot go, especially in terms of hardware,
Right.
beyond what they are doing.
Exactly.
Maybe you would like to do different kind of optics and different kind of things. So
Right.
It's interesting.
So maybe that should be a project, how to get around the patent.
Oh.
How to invent technology that gets around the patent. That's the question here?
This is it.
Oh, you have one? Oh, excellent. Do you mind passing it around?
No.
Yeah, just pass it around. All right. And then we'll talk about Bow Codes, which is a project with Ankit Mohan, Grace Wu, Quinn here, and Professor Hura, who was here last year. And the idea is, how can we exploit properties of cameras for objects that are very far away? How can we add intelligence to the world so that the world is more compatible with billions of cameras people are carrying? And I won't go into the detail, but the basic idea is to convert a point that in sharp focus looks like something that is the size of 3 millimeters by 3 millimeters, and take an out of focus photo, I think I saw it last time, and convert a circle of confusion into circle of information. And we'll look at motion capture solutions for HCI, some other solutions we have built here for kind of inverse optical motion capture, and some other HCI devices. So we'll spend a lot of time on that. So an announcement here, Shahram Izadi, who is one of the leaders in using cameras for HCI, is giving a talk actually on Monday. This changed. On Monday at 4 p.m., I believe in the Roth room. And he's the inventor of, if you're familiar with Microsoft Surface, which is a tabletop surface with a projector and camera underneath, he built a version that's a variant of that, where they put a screen. The screen is actually not diffuse, but it's switchable. It switches between a diffuse screen and a transparent screen electronically. So in one frame, you're projecting an image on it, and you can see it on the tabletop. In the next frame, it switches to become completely transparent, and the camera underneath can see the world through this diffusing, through the screen, and you can do some gestures on top. And again, in the odd frame, it goes back to being a diffuser. So he'll be talking about that. He just received the TR35 award from Technology Review. So he's here in town for that, and he'll give this presentation on Monday at 4 p.m. I believe I'll send out an announcement, but I'll send out one more. And our own Praveen Mistry, who built this really beautiful Sixth Sense display, also got the TR35 award. So those of you who are not familiar with his work, really great HCI projects can lead to TR35 awards. All right. Then we'll spend quite a bit of time talking about scientific imaging and computational imaging in sciences. And this is something that I've heard a lot of times. New instruments lead to new discoveries. And in the 20th century, probably the most important instrument was a computer, right? And what we might see in the future, in my biased opinion, is the most important device we'll have is a really important imaging mechanism. We don't know what it will be, but it could be some permutation of a combination of what we are studying here. So computational imaging has led to, it has just transformed our world. Unlike a lot of fields we know which are really important. If you think about just Nobel Prizes, my background is in computer vision and graphics, and there have been no Nobel Prizes in computer vision graphics, and not even Turing Awards in computer vision or graphics. Pretty sad. But if you think about imaging, there have been tons of Nobel Prizes in just purely imaging mechanisms, and we'll be studying them. Phase contrast microscopy, a lot of CT scanning and MRI and so on. So I don't know why important fields like graphics and vision are not getting as much attention, because we are solving very important problems as well. But maybe it's not being pitched right, or there's something more there. Anyway, so we'll study computational imaging in terms of medical imaging, astronomy, applied physics, and biology. And a lot of these ideas are, as I said, applicable across different fields, whether it's photography, HCI, computer vision, and so on. So we'll study tomography, confocal microscopy, and so on. All right. So let me switch over to today's topic.